So in this third introductory segment, well, fourth actually, I'd like to ask the question, why analyze passive tissue instead of active? In the subsequent segments, you'll see that we do a lot of analysis of different kinds of stimuli, and we generally assume the tissue is passive rather than active. Well, everybody knows that the tissue that we care about is active tissue. So why are we analyzing passive tissue instead, or at least assuming passive properties in the course of the analysis? There's a good reason for this. It's definitely not because there's no interest in active tissue. In fact, active tissue is our main interest. But when stimulation is for the purpose of initiating excitation, which is the single most common application, the tissue begins, prior to being stimulated, in its resting state, and in its resting state, it functions as if it were passive. It's not performing any active processes. So assuming that it's passive is a good approximation. If you recall back in our slides that show the beginning of stimulation, the first little deflection that comes from the stimulus is the deflection that you'd expect in passive tissue. It is the subsequent changes that constitute the action potential. So passive is very good. Then, secondly, many modern stimuli are short. That is to say, they're precisely controlled in their duration. They're often less than a millisecond and sometimes only a fraction of that, say 200 microseconds, 300 microseconds. That means that the tissue does not have time to change its state, does not have time to change the probabilities very much. Throughout the stimulus, the tissue retains largely the properties it had at the beginning of the stimulus. So while one may not assume that it's passive in the sense of having resting properties, one can assume it's passive in the sense of having unchanging properties electrically throughout the course of the stimulus. And then the third major reason is linearity. Linearity is a big reason as far as analysis. So many, so important, I gave it its own separate slide. Let's go to that. So linearity in the context of stimulation relates to the mathematical analysis of what is happening. Linearity means that the voltage changes of the membrane that are produced by two or more simultaneous stimuli are equal to the added results of each one separately. Now, of course, normally that's the case, because normally the analysis includes at least one source and at least one sink. So there are at least two. There may be more than that, depending on how electrodes are arranged or distributed. So linearity cuts the work in half. Sometimes it cuts it by more than half. It's a very powerful and useful tool. On the other hand, linearity is only present with passive tissue. So if passive is a reasonably good approximation to active, the benefit of linearity tends to outweigh any loss of precision associated with that assumption. So we are very, very happy in analyzing stimuli to be able to have linearity on our side. So in the subsequent slides, we're going to analyze several geometric arrangements of stimulus electrodes and tissue. We're going to use spheres, we're going to use cylindrical cuff electrodes, and then a field electrode near a cylinder. These different geometries are not simply a list, but the best geometries for illustrating different principles of stimulation. And because their different principles are illustrated, not just different results, you'd have to say that every geometry gives insights that are useful to all the others. because in the others it may not be as clear, but it is still present. Not only that, these geometries are idealized perfect geometries, but they're not geometries that have no relationship to the more complicated geometries that are seen in humans or in animals. So the insights that we gain from these idealized geometries are good insights that can be used in real stimulation, just as much as in these particular cases. Of course, the precise mathematical results can't be used, but the idea of the results can very well be used. Blue flowers, as you know, are special flowers, and here's a whole armada of blue flowers on display in the Duke Gardens. Thank you for watching this segment.